Good evening, everybody. We are starting our next season of the Advanced Programming Specialist Group. This is taught by Russel on Java type languages, where will be shown some information plus demonstrations. Additionally, just as a small announcement, we are planning our annual general meeting for November, and I would like to ask if somebody would like to volunteer for the committee. Please let me or some other members of the committee who will see with the badges walking around, let them know and discuss opportunities, what you can do in terms of the working this committee. There is no planned any alarm training, so if alarm will go off, so please go to one of the exits there, and let's start. Russel.
Apparently I need to use the microphone, but I also need to use both hands. I'm used to having a headset mic in that situation, so this is going to be a bit weird. Okay, so some people are in the wrong room. That's fine. They're obviously not interested in programming, they're interested in management. Okay, so here we are. That's me, but usually, of course, people have slides and spend hours explaining who they are, etc., etc. And you can see I'm X everything, because like 1 or 2, I'm retired, but I'm not yet an ex-human being. Hopefully, anyway.
Not quite as beautiful as you once were.
Yeah, I also go for the t-shirts, which is pretty good stuff. However, I think I just did want to brag a little bit, mostly to give you the confidence that I do actually know what I'm talking about when it comes to these languages. So, sort of a couple of seconds on the personal history. So, you know, sort of late 60s, early 70s, you had to do Fortran, unless you were doing COBOL. But as I was a physicist, it was Fortran, and it was Fortran 4, luckily. But then, you know, you've got to descend to assembly language because it's got to be fast. And then you discover Fortran compilers are better than handcrafted assembly language. Then I went for the full thing of Algol 68, which is still one of the most beautiful languages there is. It's just that the implementation now, Algol 68G, is just a wee bit not up to scratch in terms of performance. The others, Pascal, C, C++, is sort of fairly standard sort of foray into what was then the future of the software for high energy physics. They gave up on Fortran and went for C++, so most of the code at certain places like that is now in C++. But by then I was at UCL, and we were trying to stop Pascal programmers from programming. We wanted them to learn something good. Paul Otto and I decided that we were hacking so much with Pascal to try and teach curriculum that we had to go elsewhere. And we ended up with Scheme and C++ as a combination. That worked really rather well. We were really very pleased with that as a combination. Then things moved on, and we got to the Miranda, and then Haskell, which I guess a few people might have heard of because it's actually being used around here in London, particularly in the finance community, and a few quants quite like Haskell. But then come 1994, we get the Java revolution, and there was a sort of a mental blank amongst educators, and they suddenly ditched all languages and only taught Java, which was good for Sun at the time because it really increased their revenue. Then I discovered Python properly, and well, that was the end of teaching anything in Java. So I spent a long time training people in Python, mostly in hedge funds and quants and people like that, because they're the only people who can afford me. But then there was the sort of Ruby thing came along, and I guess everyone's come across Ruby on Rails, and the hype and the complete descent into nothing else exists, which still exists in some places. But then we've got the Groovy thing, which is still going. I've pulled out of it slightly now, but it is still going, still there. Scala, 2003, 2004, came along, revolutionised the JVM. We'll talk about that in a short while. I then went for Go on the grounds that native code, you just got to do it to get away from JVM for a while. I'll have a look at Frege, which is back onto the JVM. It's Haskell on the JVM, which is actually
Why
quite
is it
cute.
named after a German mathematician?
I have no idea. Presumably because the guy who rewrote, well, there was Jaskell, which was a project which sort of is clearly Haskell on the JVM, but he didn't like that, and he is German. He wrote a new language. He called it Frege. I should have asked him, shouldn't I?
Yeah.
Then we get the Kotlin thing, and that's JetBrains deciding that Java was a waste of time and effort and far too verbose, and what they wanted was a new language. They tinkered with Groovy for a while, and then went with Kotlin, invented it, and we'll speak more of that as we go through. Ceylon will get a mention, but sadly it's sort of, it hasn't died, but progress has sort of stopped, and there's been very little evolution over the last year, which is a bit sad. Of course, you then have to do the web, which means you have to do JavaScript. But actually, one that's missing from there is Elm, which is Haskell that transforms into JavaScript, which is really very nice. And finally, Rust, which is the language I'm doing most with at the moment. Back to native code, back to doing things with televisions, digital video broadcasting, DVB-T2, and DAB Plus and stuff like that. But the interesting thing there is the evolution of the JVM as far as we're concerned here today. Gratuitous slide of squirrel, because Gail Hollis insisted I had a slide of squirrel. Talk about it later. So that's our proper introduction. So here's a little bit of Java history. And where did people start doing things with Java? 1995. So you're way down here, person. Yeah. Along with all educators who just sort of had a mental blank in Java, which was quite amusing. Obviously, we are now here. Everyone on the planet should, of course, be using JDK 11 now, because it's the only Java. It's like standards. When a new standard comes out, no previous standard exists anymore in ISO and stuff like that. So now that JDK 11 is the standard, no other JDKs exist. One should remove them and move on. Except that I think there's quite a lot of people still trying to get across that hurdle. If we take it realistically. I have to admit, I have now deleted JDK 9. It's gone. I do have JDK 11 as my main JDK, and I'm waiting for tomorrow when I can put JDK 12 on. You're not finding that funny, are you? No. Okay, never mind. Some high points which are important for talking about evolution of JDK. JDK 5 was pretty important. It was a big revolution in Java programming because of these things, generics. So instead of just having class like flob, you could have flob of thingy. And what did they do right? Yes, you had generics at compile time. what did they do wrong? Type erasure. A complete and total disaster of the biggest magnitude was introducing type erasure. And because this is actually going on to record, I won't discuss my views about that anymore. If you want to, we can talk about it in coffee and sushi afterwards when we're not on the record. Nonetheless, Java 5, a very big revolution in Java. The other big revolution is Java 8. Are people actually using Java 8, those who are using Java? No, okay. So lambda expressions really become very important. So that's small functions as unnamed arguments, effectively being passed around the place. Really quite fun. But also method references, which is sort of Java's view of pointers to functions. That's not quite really what it is, but that's a good analogue. But the really, really big thing, as far as I'm concerned, is actually streams. Streams become more important than lambda expressions, but you put those two together, and what you get is the ability to do declarative programming. So this isn't functional programming per se, but it looks a bit like functional programming. You're doing things like create some form of stream, and then you can map things onto that stream using some little lambda expression, and then you can maybe map it a bit more, and you can maybe filter it a bit more, and you get a chaining of functions. It's basically a pipeline. So architecturally, streams and pipelines are intimately related. You can create a stream going in, you can map on it, you can filter on it. And anyone who's done any Lisp will be saying, or functional programming, will be saying, oh, can I do map on filter of something, comma something, and so on and so forth. And it's that style of working. Here, it's prefix functions, or standard function application. With streams, it's a sort of fluent view of you have an object, and then you apply your map to it, and then you apply your filter to it, etc., etc. Completable future gets mentioned, not because futures weren't available. Java already had futures. I've forgotten exactly which version it came in, but it was probably Java 7, or Java, it might have even been Java 5. So the idea of having a future, which is an object which can represent a future value that will be delivered at some point, was available, but it wasn't as easy to use as you would like it to be. And completable future brought in the idea of promises, futures, made the whole thing that much better. And in the abstract, enables Java to do asynchronous type things. And that becomes really important later on. So just having a look at the bit of Java history again, I've marked in red what I consider the current critical points in Java. Green, any idea why that one might be seen as something a bit special? That's when collections got introduced. So there weren't any data structures of any note until Java 1.2, which was sort of a bit of a missing link, really. A lot of people will say, oh, Java 9's got to be a big thing. No, it just introduced some packaging changes, the module system. And the world still hasn't come to terms with the module system. A lot of people are still using OSGI. But at some point, maybe in Java 28 or something, they might eventually find out how to do these things. Java 10 turns out to be quite interesting because it introduced var. And we'll have a look at that in a minute. It's trivial in one sense, but with the type inference that it brings along, it actually changes the way you think about local code and the code within functions. And it's a surprisingly interesting change. So sort of trying to summarise a little bit here. Java is old. It was what, 23? So it's actually allowed to drink, even in America. So that's good. It is very, very imperative language. So it's all about instructing the computer what to do. It claims to be object-oriented. It isn't. We'll come to that shortly. It claims to be the paradigm of object-orientedness, whereas originally that was actually Smalltalk. And then C++ tried to say it was object-oriented, and then we had the 1990s, and then people stopped taking drugs and started deciding, let's actually talk about what these things are, and C++ decided, no, it's not really object-oriented, it's multi-paradigm, etc., etc., etc. We're still left with Smalltalk as the one true object-oriented language. Okay, so we saw on that list a claim that it's evolving very slowly, well, except that we've had Java 9, 10 and 11 in a year. So that's sort of, actually it's evolving slowly rather than very slowly, which is a monster change for Java. It's following C++. C++ used to have 10-year cycles. Now they're 3-year cycles. And hopefully they're going to be 1-year cycles eventually. The Java platform, mature, it's nicely hardware independent, and that's really what it's about. The JVM is about commoditizing hardware, so that the hardware vendors have no control. And so it's a political position, or a business position, that JVM holds within the milieu. And it evolves very, very slowly. But as with the language, we can delete one very. Because with the 6-month cadence that we've got with Java releases, we're now down to the JDK itself, the JVM itself, actually changing a little bit more quickly.
Do you know anything about Oracle's current attitude to Java?
It's changing rapidly.
I was going to say, because they were not interested in it a few years back.
Oh yeah, but that's because they didn't know what to do with it.
Yeah.
And then they discovered Java Card as an income stream for a while. They thought, oh, we like Java Card. And then that income stream sort of died away. And Oracle then decided, what are we going to do with this? Sacked lots and lots of people. But then the user group stepped in. The Brazilian Java user group and the London Java community effectively stepped up, got themselves elected onto the driving committee. The spontaneously forgot what the JCP, and started doing stuff. And so in particular there's the Adopt JDK program, which comes from LJC, and a whole load of other activities that caused Red Hat, IBM, and one or two of the others to actually pull their fingers out and decide that OpenJDK was the core platform, and that Oracle's JDK was simply a bundling of stuff for Oracle, and that has turned, I believe, from now on into effectively a support program. So there is no more Oracle JDK per se. There is OpenJDK with Oracle support. But that's a belief statement. We'll have to see in the next few months how it actually pans out. But in the main, OpenJDK is free for all uses as long as you stay within the Do you know, I'm not sure what the licensing is on it now. But there is a formal open source license for Open JDK. And that's the one that everyone's using. Of course, IBM has its own implementation of JDK, and people will have to buy that. Oracle have their own implementation of JDK, and people can buy that, or rent it rather. You can't buy it. Okay, after that very useful little introduction, it allowed me to say a few things that I wasn't going to say, but excellent. People have now read the slide. Why is Groovy in there twice? Okay, so look at it. Java, Scala, Kotlin, Salon, Frege, Groovy, Phantom, Gosu. What's the commonality there? Versus Groovy, Clojure, JRuby, Jython, Golo. What's the commonality there? Okay, these are statically typed, and these are dynamically typed. Or in one case, in the ... almost not typed at all, which is actually hard to do on the JVM, surprisingly. And Groovy is in both, because I wrote this slide when I was pitching Groovy to people. I thought, I'll just do it anyway. Because you can do Groovy as a statically typed programming language, or you can do it as a dynamically typed programming language. Okay, so a little bit of philosophy, because that's why we're here. Is change good? Let's have a show of hands. Who thinks change is a good thing?
Well, if it's the same for the better, then yes.
Who thinks change is a bad idea? Probably the same people bring their hands up, because it is a very schizophrenic thing, because it depends on the context, depends what you're doing. But I'm going to suggest that the two principal positions that people will take is change threatens, in the sense of we like backward compatibility, and in which case change is a bad idea. Because as soon as somebody changes something, there's a difference between where you are and where somebody else is. On the other hand, people like change because you can bring new things, you bring new programming techniques into the bag. And therefore, change has to be a good thing. Because if you don't have change, you end up with the Fortran compiler, which still has to compile 1960s Fortran 2 code. That is a requirement of the Fortran compiler. It is that backward compatible. And why is that? Because there are some Fortran codes out there that nobody refuses to change. Now, in the main, I think that's a bad idea. But in one or two cases, there's Fortran code running nuclear power stations. And it's been proved using Z and all that sort of stuff. And you don't want to change it because you've then got to go through the whole certification process again. And it takes 3 years. Or it took 3 years last time they did it. And so one change to a piece of code, 3-year program. No. So for those sort of people, backward compatibility, you are going to not change your code. But here's a sort of counter-example. If we go the full hog for backward compatibility, the only thing we would be writing is machine code, because that is the only one true way of instructing the computer. But all of a sudden we didn't like that. So assembly languages come out, or autocodes, or lots and lots of nice 1950s labels for this sort of stuff.
But if you wanted backward compatibility with machine code, you would never have a new instruction.
Quod erat demonstrandum that backward compatibility is a bad idea.
Yeah.
But in the 50s, we got the split. Well, the logic languages came a little bit later. But we got the split from functional and procedural, exemplified, in fact, by Fortran, which we must spell like that at this stage, and Lisp. the logic languages up here, I'm going to exemplify with Prolog, and that came a little bit later. But we got those changes, and we got object-oriented languages, Smalltalk. If we weren't allowing change, we wouldn't have these. So I would argue.
Do you think that logic languages were a dead end?
I'm going to say yes and no.
All right.
Yes, they're a dead end because they've not had that much take-up, so they're not really populous in the world. But no, because they are a massive paradigm of how to do a certain form of computing, and they had a huge influence on the AI community, and that was worth having, and is still worth having. And there are still Prologs out there. Further questions?
I mean, some of the Prolog features have filtered into other languages. I mean, pattern matching, I mean, in Erlang and so on. So the ideas have got there, even if it's not really, it's combined.
And indeed, I suppose I ought to be repeating questions for the microphone. Apologies, I've not been very doing that. But I think your point is well taken. That features of Prolog have crept in other places, and the most obvious one is that Erlang was originally written in Prolog, which is why it has a quasi-Prolog syntax. And then they re-implemented through the Beam engine, which is really a lovely label, the Beam engine. But I'm arguing here that backward compatibility is the enemy of progress. A slavish restriction on backward compatibility stops progress.
Well,
But also,
what if it breaks something that already exists?
we like breaking things.
Not if you're a user.
We're not at user level yet.
I mean, there are a lot of people who are not exactly in your nuclear power station paradigm, but not far off.
But I think last week, or yesterday and the day before, was Jack's London, and earlier in the year, Devox UK, and now we're getting Devox in Belgium and stuff like that. And 99.99% of the people are doing well. And their, this slavish attention to backward compatibility is actually counterproductive, big time.
Right, but I mean, just a slight digression, but most commercial application implementations are actually made of lots of bits and pieces, some of which may require to be very stable, and others of which may actually want to change quite quickly.
Yeah.
So,
but in the end, that's what continuous integration is all about.
Yeah.
And if an organisation has software and no continuous integration, they are doing it wrong. There's no mealy-mouthing about this.
Yeah.
Continuous integration, and indeed continuous deployment, is what all organisations should be doing. That doesn't stop some part of their software being very stable. But it does imply that it should be on continuous integration all of the time.
And it also means that you are going to have multiple languages in any actual real system.
Most of the time, yeah, absolutely. I put this point up here to have a go at the accountants that run most of our companies. They often think, don't change the software because it means more work. More work means more money and less profit. But it's also a horrible place for programmers to go. They say, I don't want to change this because that will mean more work for me. And that's not the modern way of programming. The modern way of programming is small changes, continuous integration, get stuff out there. Keep the software live at all times. Keep it moving at all times. I'm going to throw this one in there. They're saying that if the world is moving on, if compilers are changing, if languages are changing, and the core software is staying stationary, there is a mismatch between them, and you end up with the world of Fortran, where your compilers have to compile 50-year-old code. And I'm going to say that in the modern world is a bad idea, except in one or two really very, very niche situation, which is why I mentioned the nuclear power stations, because they are a very, very niche position. And so that ends up with this question. Java was evolving slowly, and it was obsessed with backward compatibility. I mean, completely obsessed by it. To the extent that it never removed any deprecated bits of the API. Okay, so in 1994, it introduced the threads, which was sort of a nice idea. But one of the things was start a thread. Yeah, okay, that seems like a good idea. Yeah. And another part of the API was stop a thread, which anybody who knew anything about concurrency from 20 years beforehand could tell you this was a total no-no. I'm going to put this down for a moment. You can't stop a thread externally without destroying the entire theory of concurrency. And there it was. So, okay, in 1995, I think, it was deprecated. It's still there. Because backward compatibility. Oh, we've got to do the thing the accountants want. We've got to make sure that any Java code runs. Well, that's a threat for a start, because your code is broken if you're using threads, because anyone can stop any thread from outside the thread.
So could you just argue to the accountants that this is a safety exposure?
Any API that allows a thread to be stopped externally is just a security loophole.
Yeah, so there you go, there's the counter argument. To the money man.
Yeah, go for it.
Yeah.
We have to spend money. We need to do.
Which
The core problem with the business angle on software is that the business angle is that it is not recurrent stuff. I'm losing the words I need here. But in terms of the bookkeeping, they don't treat it as recurrent budget. They treat it as a capital asset.
Yeah.
And treating software as a capital asset is the wrong thing to do, because it's in the wrong place. If you treat software as recurrent budget that you're posting people's time against, then you can very quickly move to continuous integration, continuous delivery as the way forward. And I would strongly recommend people to have a look at, not yesterday, but the day before's Jack's London keynote. When was it? Yeah, I'll have to post it. I've forgotten which one it was. But the person was talking about how continuous delivery is the right model for programmers' psychology and cognitive working. That any other, waterfall style, is so counterproductive for the cognitive process, and that continuous delivery is the right way of working with software. But that only works if the business treats the software as malleable asset, not as capital asset. I'm using slightly wrong words here, so the argument's probably not being made quite as well as I could make.
I mean, Tony, I'm sure you would acknowledge that all assets have a much shorter lifetime now than they used to in the past.
Yeah, the software is like hardware. It's depreciable.
Yeah.
What's the treasury for 60 years?
Which is not.
Well, hardware's deprecated over 3 years. Why is software still deprecated over 50 years? Anyway, let me progress. Moving on. So we must separate Java the language from the platform. Why? Because the platform still serves a purpose. And if Java won't change, then what you do is, and I precursored this already, We change the languages. And we put small talk here. Whoops, too many dashes there. Java likes to think of itself as there. It isn't. But what do we want to put in here? So what language on the JVM moves us from being either object-oriented or functional and brings the two together? So whether Scala is still used, it has a role in the history of the Java platform. It revolutionised the way people thought about code by integrating bits of functional languages and bits of object-oriented languages, and that is a good thing because it makes stuff more declarative. And that again is feeding into the cognitive side of programming. If we can get away, if we can abstract from things like threads and so on, we make our software more secure and less prone to bugs. However, while Scala was 2004, really, when Scala hit the scene, and has been progressing ever since, now up to 2.12.7, I think, something like that at the moment. It's great. It achieved the revolution, but at the expense of being somewhat overcomplicated in many people's minds. Some banks went for it. About 2011, some banks threw out all their Java monoliths, or most of it, and went for an architecture where it was Scala at the core, surrounded by Python. So there's a lot of Python out on desks, talking to a central Scala core. So you can see why I got a lot of Python training in.
We even extended it.
Sorry?
We even extend the Python language.
Yeah, indeed, yeah. And Tony's company was not the only one in London using that sort of architecture. I got a lot of nice trips because when you do work for banks and they send you overseas, it's a question of whether you go business class or first class. So many actually did take to Scala and great proficiency at it, doing a great job. But many found it very, very unsatisfactory. And so Kotlin comes out of JetBrains, and their thinking was, we don't like Java, we've got this huge Java code base in terms of IntelliJ IDEA and the spawned versions from it, and they wanted a language that was less verbose and faster changing, had more modern features. They looked at Scala, which had the revolution in it, mixing functional and object-oriented, and they did not like it. They thought it was overcomplicated, too heavyweight. They had a look at Groovy, not dynamic Groovy, because that would have been way too slow for them, but static Groovy. But it wasn't quite ready at the time. And there were some awkward corners to that whole idea of entire Groovy code bases being statically typed and statically compiled. And that's what drove JetBrains to invent a new language. And for those who don't know, Kotlin is actually an island just off St. Petersburg. And that's why the language is called Kotlin, because the St. Petersburg office of JetBrains looks out over the island. You didn't want to know that, but I thought I'd just put in a little bit of stuff. Where's Ceylon come from? That's Red Hat. Small little project, but it got quite big for a while. Red Hat. It's called Ceylon because it's tea as opposed to Java, which is coffee. And these two languages in the static compilation camp for a while drove evolution. So what are the sort of headlines? Well, Kotlin very much wanted to be incremental change. You've got a Java code base. You want to add new bits to it. You want to do it in Kotlin. You want to take Java bits out and replace it with Kotlin so that you can do an evolutionary change over your code base. You don't have to do a revolutionary change. And that was a big driving force because JetBrains had a lot of Java code they didn't want to change quickly. They wanted to change it, but in an evolutionary fashion. Back to the CI and continuous delivery mental model. As I pointed out, influenced by Java grew in Scala, and they improved a lot of things, and we'll see some examples of that. Ceylon was much more a replacement because the type system is so different in Ceylon to that of Java. And yet you can access the Java platform. What's the point in having a new language on the Java platform if you can't access the Java platform? And so it was made to interwork, but not as neatly, in some sense, as Kotlin. And yet the type system in Ceylon is actually really cool. You can compile them to JVM or JavaScript, so hidden behind this is the web and wanting to replace JavaScript as the one language on the server and one language in the browser type thing, mostly because Node just, well, was a fashion item and we've gone beyond it now. None of you folks are JavaScript Node people, are you? No. Good. Okay, so I can slag JavaScript up even more. But the idea here is that end to end. You write your server in Kotlin, you write your client in Kotlin, and transpile it to JavaScript to ship it down into the browser. So we're after the Scala revolution. We've got lots of type theory. It's all 2010 stuff going on. And of course, we have to do Hello World because, when was it, 1977 or something, the book came out, C Programming Language, and Hello World was it. Let's just do it. Okay, so here's Hello World. I'll have to change glasses now because I can't actually read this anymore. And so here's our Java. I think everybody's seen that far too often. This one is the Kotlin, so you'll notice no classes because top-level functions, because why should the programmer write them unless they have to? If you're going to create a class, create a class. Why should you have to create a class? Simply to have a top-level function. It's the compiler's job to deal with that. So that's the difference between 1995 thinking and 2010's thinking. Make the compiler do the work. Ceylon has gone one stage further because Ceylon was around before the big JDK9 change. So JDK9 brings in a module system for Java, and Ceylon already had a module system. Ceylon was founded on being module-based, and there was the JBoss module system from Red Hat, and that Ceylon was built on top of that. I'm not really in the sort of modules arena, so I can't talk much about the JBoss versus the Java module system versus OSGI. But that's the battle that's coming. And I fear that JBoss may well disappear. But we will see.
So Russel, for an idiot like me, can you explain what share does in the one on the right?
It's to do with the module system. And it's saying this symbol run can be seen outside the module. So that it can actually be called from outside the module system. And your entry point has to be a symbol that's known from outside the system.
So it's just exporting.
It's basically an exporting system, yeah.
And it appears not to have any types in it at all.
Well, void, but the arguments come through a different system, so come through another module. There's a question back there.
Yeah, I mean, it's more a snarky remark. I've got to say that I find these examples a bit, well, I mean, they're peculiar because, well, the main program forms what percentage of the whole code base? A very small one. Now, I mean, well, I've seen this, well, in Java, the Hello World program has like 5 lines because you have a class containing, a method containing the Hello World line. In Python, you only have 1, in C, you maybe have 3. But the real question is, well, if you have a code base of 1 million lines, if you translate it to Java, does that mean 5 million lines? And
No.
the answer to that is no, it means 5 million, no, 1
And
million
one. Yeah, yeah.
lines. And that is a rather negligible difference between
I
the
agree.
languages.
It's just that these are the fastest way of showing this feature and talking about compilation as moving forward.
Okay.
What we need to do, you're quite right, this is just the one place that something happens. It was just a hook. And it also allowed the joke about Koenig and Ritchie. However, examples do have to be small. And I am going to be challenged by your challenge of the 5 million line code base in order to keep the examples visible on the screen. So you'll have to excuse me of slightly undermining my arguments by having small examples. I'm going to have to speed up a little bit, as otherwise we won't get the examples in. Okay, so let's ignore that bit. So we have to do Fibonacci. 3 reasons for this, and the smallness won't be a problem because we will get some really interesting examples. Put that down again because I need 3 fingers to get down here. So here we have some Java. As everybody knows, factorial and Fibonacci as numbers explode very quickly. So factorial of 24 can't be computed with ints. You can't do it with hardware. So you need software numbers. Factorial doesn't get as big quite as quickly, but if you want to do things with Fibonacci numbers, then you're going to have to use big integers. Now, my justification for even thinking about factorial and Fibonacci is that in some of the models that quants use in some of the hedge funds, factorial and Fibonacci numbers are actually crucial to some of the models, and they do need to compute them and use them. And so you're finding, you mentioned Python. Python doesn't become a problem because the Python virtual machine unifies hardware integers and software integers quite nicely. Whereas on the JVM, there are the JVM hardware, in inverted commas, integers and big integer. But there's some code here. The obvious iterative thing, notice I'm using var because JDK10. We don't have to specify the types, the compiler does the type inference. So let's use it, let's do it. But it's the classic algorithm that we've got here. But notice we can't do I equals I plus 1. We have to do I dot add 1. Why? Well, it all goes back to 1992, 1993, with a decision made by the Java development, the Green project, the Oak language, decided that operator overloading was too complicated for programs to deal with. Therefore, they wouldn't have it in their language. So you can't overload operators in Java. Every other language on the JVM has introduced operator overloading, which I think tells you something. The other examples down here are less interesting simply because they are quite boring. Naive
So it
recursive.
wouldn't break backward compatibility to introduce it.
Now that let me stack that one for a minute. Usual stuff about memorization, and the closed form thing. Here we are. That's where I was.
Sorry, what you were saying about naive recursive?
It's the naive recursive has an order n factorial behaviour in time.
But that's just the name of the thing.
Yeah.
It's not a keyword or anything.
No. Naive recursive is just the name of the function
Yeah.
for calculating,
Okay.
and it uses the classic first-year undergraduate algorithm that people still remember into their 50s, and it's just completely useless to man and bees, especially if you do it with ins. But I wanted to show the memoize simply because it gets round the tail recursion problem, because most people say, oh, normal recursive not interesting, tail recursive must be the way forward. But the JVM doesn't support tail recursion. So that's not really, but you can do it with memoization. And so there are interesting ways of doing memoization on the JVM that enable you to get rid of that order n factorial performance.
How would you wouldn't be able to if you were writing with tail recursion anyhow? It's not. It's process is intrinsically recursive.
But tail recursion allows you to do it. And Scala and Kotlin and Ceylon all have mechanisms using continuations of creating a tail recursion on a platform that doesn't support it. But I did want to just show the closed form because it shows you that fluent approach to being able to build up pipelines of things going on. So we're using the squirt5 is some value of, gives us an object. That object you can add, you can divide, pow, and so on and so forth. And that fluent approach is core to the modern way of thinking, and is core to the way of doing things with streams when we come to it. Okay, I want to cut short having a look at the Java so we can have a look at some other languages. In particular, we have to look at Scala. Simply because we do. So what did Scala bring? Well, long before JDK 10 introduced it, Scala had val and var. Var, variables, type being inferred. Val, effectively final. Now, Java has been a single assignment language since 1993, just that most Java programmers don't use it. I gave a talk at Checks London a couple of days ago. I asked the audience, how many people programming Java use final on all of their variable definitions to use this single assignment, which is integral to the Java language? And a third of the people put their hands up. So that means 2/3 of Java programmers are not thinking single assignment, which means they haven't even into the 1990s in terms of managing variables, which is very sad. But what Scala did was to reinforce this separation of a binding from a variable. Straight out of functional programming, bindings. Names are references to values that you cannot change. And so val 0, a value I cannot change. We like that. It did also change the way you specify types, so that's where the Pascal type structure has come from. That's just prejudice, I think. You either like it one way or the other way. And it's an infinite argument. It's bike shedding. You just go with whatever the language chooses. And we see the iteration with while, and for is not actually iteration. It's, no, let's not go there. You could spend 50 minutes talking about in Scala. But it looks like iteration, but it actually isn't. And then you can do naive recursion, and then you can do tail recursion. And there's the at-tail rec, which is, remember the JDK underneath, sorry, the JVM underneath cannot do tail recursion. So it's a construct built by the compiler using this annotation that allows it to define a tail recursive system. And tail recursion, going back to your Lisp, state is carried in your parameters. There is no state outside, no changeable state at all. And so tail recursion is the one true way of doing iteration in a functional manner. And so we've exemplified this functional versus iterative approach. And there they are in the same language, exemplified. And this fight between when do you use an iterative approach and when do you use a functional approach is still going on. I also did the memoized recursive, and then we introduced sort of fold, which is it's really a reduction. So many languages would call it reduce. A lot of Fortran people who do distributed computing, parallel computing, know all about reduce as an operation. Reduce is in Lisp, and so on and so forth. It is the same operation. You have a sequence or a data structure of objects, you reduce them by one dimension or 2 dimensions. And fold is just another name for effectively the same reduction operation.
When you say the battle is still going on, I mean, it used to be performance was the key difference between function and everything else.
Yeah.
Is that still part of the argument, or is it purely stylistic?
Stylistic, because the compilers can now construct better code for these fold operations than you can for your iterative code.
Really?
Not always, but usually. And if you look at the way C++ has evolved, and you look at standard library, the application section of the library, that can produce brilliantly tight code.
Do they compile to the same thing, though? I mean, tail recursion become a loop.
Effectively, yes. But it depends on the library, and so you'd have to go and ask John Wakely what he's doing now with the C++ library. But some of his code generation in GCC and the Clang code generation means that declarative code can often produce faster computation than handwritten imperative code. And the the TBB, for example, is a big library in C++ written by Intel. And if you write good TBB, the compiler will then actually get close to microcode in producing the resultant computation, because it will actually tinker with the microcode going in.
I think in parallel I see it using AVX instructions.
And it's really quite scary stuff. Okay, we haven't got to Kotlin yet. We must get to Kotlin, and we actually ought to be getting to some more complicated code by now. But let's forget Groovy. Do we want to have a look at Ceylon? Yeah, well, let's have a couple of little things about Ceylon. Notice they've got union types. Oh, fabulous stuff! This actually makes writing generic code really cool, because you can write code in here, and you know it's either an integer or a whole. You're not having to worry about horrible inheritance or using traits or anything like that. It's a really nice way forward. I actually got into Ceylon big time simply because of these union types. It makes writing code really nice. They have a different view on switch and case, stuff like that. These are just differences from sequences they're blocks. But it makes for nice looking code. But in the main, you know, you can do your iterative thing. You can do your recursive thing. You can do your tail recursive thing. And then I stopped because Ceylon was sort of not really progressing for the last year. So it was that. So we get down to Kotlin. Whoops, wrong one. Why is Kotlin important over all others? Google. Yes, Kotlin is produced by JetBrains, but probably the single biggest platform at the moment is Android. And Android runs Java 6 with some Java 7 bits in it. And there is a battle between Google and Oracle involving tens of billions of dollars. And so Google, now I am speculating here, I don't have any inside knowledge, this is pure speculation from observation of what's going on, that Google has decided to stay with the current JVM so they can avoid any and all fights with Oracle. But they wanted to improve the programming language. So rather than using Java, they tell people to use Kotlin. And indeed, they support it in the Android IDE is well supported with Kotlin.
With the recent developments and Oracle more or less releasing the JVM, I mean, would that change things in the future? Do you speculate, or?
Oracle have sort of released lots of stuff, but OpenJDK was already there. So what Oracle have released is actually a bit of a marketing stunt. It's actually a very small amount of stuff.
Well, at this point, Google would be pretty safe if they were just using OpenJDK and build whatever they want into Android, isn't it?
Yeah, I think it has changed. And the Microsoft release of patents is actually more important to Android than Oracle releasing their JVM code. So the next year is going to be really, really interesting in terms of the direction that Android goes. But in the short term, that's a medium-term thing, because all the lawyers have to sort out their positions before things can happen. But in the short term, Google have backed Kotlin as the language for Android because it brings all these new functional approaches to the platform now. Whereas anyone using the sort of Java 6, Java 7 mix that is available on Android have no access to all this new way of thinking and this new approach to programming. And here I'm showing, look, I can 2.bigint. I quite like that. It's a constructor. Again, you've got the var type stuff that Scala brought with us. Ranges and a nice way of expressing for loops. You've got whens, so this is case selection. And you can do lots of interesting things with that. That's come out through the ML family of languages. That's really quite nice. Yes, they will do tail recursive stuff. Again, there's a tail rec annotation to bring stuff out on here. And then we get some really nice, interesting stuff. Lazily evaluated infinite lists. You've got to love this stuff. So FS sequence.
No other way to evaluate those lists.
Exactly. And Haskell's been doing, well, Miranda's been doing it for decades. Lisp got there eventually. And Java will almost certainly never get there. But there we are, look, generate sequence is a function, you give it a start point, you give it a lambda function, and it's basically classic Python generator type stuff. You've created effectively a sort of continuations type setup where at each stage you can pull the next result. So you've specified a computation, not a data structure. So you represent the infinite data structure with a computation. It means you then have to take it. This is straight functional programming, straight out of the standard playbook. But here we are doing it in an imperative language. So it's declarative programming. We're emphasising the point of view of declarative as a mental state for our programming. So our function sequence delivers a value which is the n+1th value from the sequence, and we take the last item off it. There's a strong relationship to memoization going on here. I wanted to put that memoize in because actually we prefer to memoize. Why? Because when you take n+1, you regenerate the sequence every time. So there are lots of imperative, declarative, computation versus data structure issues going on here. So these lazily evaluated infinite data structures are not always the right way. You might sometimes want to do memoization to create the data structure actually on the fly. And then there are coroutines. I wanted to make sure I mentioned coroutines because this is ways of building little bits of computation. I mentioned threads earlier. I'm sorry, I'm going a bit over time. I hope you forgive me. I'll try and keep it to another 5 minutes. We had threads, and in the 1990s they were lightweight, and they basically were in your process, and you had a scheduler, and you had lots of threads, and then the operating systems, well actually the hardware people, had all, that says hardware on it. Let me read it. Hardware. People had far too many transistors and didn't know what to do with it. So they put lots and lots more cores onto their processors. And then the operating systems people didn't have a clue how to handle it. So they took the idea of threads, brought them into the operating system, mapped them down onto the cores. So threads, instead of being nice little lightweight things in our processes, became heavyweight things in our processes. But instead of having a scheduler up here, you had the scheduler in the OS. And all was very cool for about 5 minutes. And then software people said, I want my lightweight threads back, please, because these heavyweight threads are just too heavy. So then we got fibers. Or if you're in America, fibers. Which were lightweight things with a scheduler in our process. How do we connect all this together? Thread pools. And then we get into really nice stuff. Because you've got a thread pool managed by the operating system with connection to all the processes the operating system can see. Your thread pools can then animate your fibers within your process, and you get the best of all worlds, because your fibers can be happening in parallel. Except that most people, when they implement fibers, understand concurrency, but don't understand parallelism. That's a whole different ballgame. But what the Kotlin coroutines do is bring you structured concurrency. So thread pools, lots of fibers, but we're doing it with declarative programming. Underneath, there's lots of stuff with fibers and operating systems and thread pools going on, but we don't care. We're just doing build, sequence, and yield. And the compiler does all the hard work and the generation. We like this. This is a good thing. Kotlin has brought it in under the label coroutines. Previously there was a package called Quasar, which has been around, Parallel Universe, I think can't remember the exact organisation. But Quasar is a Java library with fibres on top of thread pools, channels and all that sort of stuff. I was involved in GPARS, which was a groovy version of all this. GPARS has almost no resource, so that's not going anywhere. Just a second. Quasar is now being moved into Java under Project Loom. So hopefully Java will get coroutines and will get all of the parallelism stuff into the fork-join framework via that route. In the interim, Kotlin has already got coroutines. You'll notice, if you go and have a look at this code, it's experimental in Kotlin 1.2. It all becomes mainstream in Kotlin 1.3. So Kotlin 1.3 is going to be a big change for programming, especially on Android, but also on any other platform. I'll pause for a moment. There's a question there.
Maybe I'm misunderstanding something, but I don't think coroutines necessarily anything to do with concurrency. They're rather to do with controlling the sequencing.
That's exactly the point. You have a program which starts at one point, but can then spawn other things that it might want to do. And if you were working in an event loop, you'd code those up as callbacks, and then you'd have callback hell, unless you did it sensibly.
You don't need concurrency to implement any of that.
Right, but what the coroutines are doing is saying, okay, I'm building a sequence, which means this is going to be a coroutine, and the yield will return a value and stop there. Classic Python type stuff. But it's a little coroutine that's here. You can have lots of them. And the managed concurrency that Kotlin coroutines provide handles all the switching between these as and when it's needed, as events come in from the outside.
But nothing has to be concurrent. That's still a single execution thing. It's just the way. You can look at it as two different things,
Yeah.
but none of them are
But
actually.
now, as soon as you introduce thread pools, you have a way of accessing multi-core, which means that you can then put all your coroutines out here, and the Kotlin runtime system manages it all. You don't even have to think about it. You just write your coroutine code, and it manages the concurrency and the parallelism. It's not for free, so you're not getting something for nothing, but you are getting really quite nice stuff going on there. Now, given the time, I must be good to the audience and quit and wrap up quickly. So we could have looked at anagrams and word count as representative real applications. I'll put all the code onto GitHub. It's not there just at the minute, but it will be. All the factorial stuff's on GitHub. The interesting thing for me about factorial is not just the models of computation, but also the testing. And there's a lot of fun to be had in looking at the testing, and in particular, property-based testing. If you're not into property-based testing, get into it next week, because example-based testing is not a place to be anymore. You want to be into property-based testing. So just to wrapping up, I mentioned operator overloading. I shall rant at every opportunity that Java did the wrong thing, that the Java people who invented it were both arrogant and condescending to programmers by saying, "Ooh, you are not good enough to be able to handle operator overloading." You've got this idea of language evolution by replacement. Instead of evolving the language, change the language completely. Kotlin and Salon, we didn't really look at Salon. I've emphasised Kotlin because the slides were mostly from last year, but the content is not. More declarative. Declarative is the key word here. We want everything to be more declarative. And that's the big lesson of the merge of functional and object-oriented. Run on Android, target JVM, and there's lots of stuff in there that actually you can't do in Java yet, even in Java 12, because until you get that concurrency in with the fork join, it will be a bit of a problem. So that would be where you would end. However, I'm going to put an end note in that the JVM is dead, and that's why I was stalling when I thought about the what Oracle are actually releasing, because the Graal VM from Oracle is actually the new intellectual property that Oracle own. And it's not just about the JVM, it's a brand new virtual machine that has the idea of running Java bytecodes, but it also wants to run Python bytecodes and ML bytecodes or OCaml bytecodes.
That sounds like a nightmare.
Sounds like a...
Nightmare.
Actually, it's not. It really is quite cool. But at that
It's
point...
like a nightmare to maintain, all right.
I've overrun 16 minutes. I do apologise for that. But once I get going, it's very hard to stop. But I will stop. So sort of bring the formal session to a close at that point and take questions as sort of more informal basis, really.
Thank you very much. Now, question time.
I mean, it's still not clear. I mean, what is it that makes you think that Java isn't properly object-oriented?
Right, object-oriented specifies that you have a receiver, a message, and some data. So if I look at A plus B, object-oriented says A is a receiver, B plus is a message, and B is a value that is being sent to it. In Python and C++, that is realized by saying, in Python, A dot underscore underscore add underscore underscore B. That's a way of realizing that A reference to an object, is responsible for understanding the message, underscore underscore add, with the value B. In C++, that would be A dot operator add of B. But again, it's a realization of sending a message to a receiver. In Smalltalk, the syntax would be slightly different, but you would actually end up sending a real message to a real receiver. And that was the 1980s, early 1990s definition of object-oriented. A receiver received a message, and the receiver was responsible for understanding what the message was. In Java, the compiler compiles Java bytecodes for that, and you have no control over the meaning of add. And so it has abrogated your responsibility for being able to define what an operation means as a message. So this violates the 1980s, 1990s definition of object-oriented.
I mean, that is a one definition. I mean, the definition that I perceive to be the mainstream is that object-oriented is when you can declare classes, you can create instances where it's clear what each instance is. What each instance's class is, and that then leads to a rather different.
So I have a class X, and I want to create an instance of X and maybe I get a Y. Now I cannot do that.
Yeah, well, I mean, that's right, but I mean, I would consider this to be a bit of a fringe thing that, well, Java has primitive types, and yes, well, I mean, they are not first class citizens of the type system, but...
So big integer, in that context, cannot be an integer.
Yeah. I mean, when the primitive types are not properly integrated with the sort of, well, if you like, more proper object types, well, that much I understand, but whether that makes the whole language not object-oriented...
This is just one facet.
Sorry?
This is just...
Okay.
This is the killer blow, if you like,
Okay.
because
Yeah,
the
well,
compiler
yeah.
has abrogated your ability to define the notion of message.
Okay, yeah.
And that's why I had the big integer example in there. But it's to do with the type system, but yeah.
But couldn't you write object-oriented? If you never use ints and you only use integers, and if you just didn't use the primitives, more or less you could write object-oriented if you wanted.
But that's the point. You see, the compiler understands the type integer and the type int. And the type big integer has no relationship at all to them. So in terms of type theory, ints and integers, the compiler treats in a way that you could consider the same. But big integer is completely different, even though the concept is the same. Python has merged that, and, well, it doesn't have those separations.
So it should have defined big integer and integer as subtypes, subclasses of
But it
sub-others,
can't,
generally.
because overloading,
Yeah, you can't.
you can't do it.
Yeah, you can't do
But
it.
the chap at the back is quite right. This is one of the things. We shouldn't overplay it.
Yeah, overloading syntax. But what happens is, when you look, this Smalltalk's definition of a message and all this stuff, this all became, if you look at languages with inheritance, like the C++ example, when you say a.operator plus, well, it's just syntax that it's operator plus, okay? But the fact is that you don't actually know the type, you statically type, but you don't know the type of A. All you know is that A is a subtype of something that has an operator plus method.
Yeah.
So you still have this, through inheritance, you still have this notion of understanding the message. But the message, we don't know really what the type of A is. All we know is that it can understand, through inheritance, it can understand the method operator plus.
Yeah.
And so Java would do that too, but it just doesn't have the syntax for doing it.
And
It's operator overload.
But also the type system is awfully disjoint. And that's one of the things that Ceylon in particular was trying to come to terms with, was trying to make a type system where you wouldn't get different forms of integer, and hence showing whole and integer and union types of that sort. But it's there's a whole load of type theory stuff that will support the argument, but yes, there is also the syntax one, which is what I've highlighted here.
When you're at ECL, you recommend use the scheme for ML and C++ as sort of two good languages for teaching programming. What would you be recommending now?
Python as a first programming language.
And
And not only would one recommend it, the education system in the UK is already doing it. So kids from age 8 to 11 use Scratch, which is a plug-and-play language, and then from age 10 actually upwards, they use a textual programming language. And because the Python community joined with the teachers to support them before 2014, but particularly in 2014, when the government shoved everyone into a pit of stuff with no money and said, here, we're changing the curriculum, do it. Python has become that textual programming language. And so kids from 11 through to 16 are now all doing Python, as well as Minecraft.
and instead of C++, you choose Kotlin or
A good way forward ends up being Python and Java simply because there are resources out there and people willing to do it. But then you really want to get into doing either Lisp or Prolog, or Clojure and Prolog, or Frege and Prolog. Some combination of those that then challenge you in your face in a way that says you actually have to create a new model of computation. It's about the computational models underneath. Okay, so Prolog brings unification. The Lisp Clojure family, just well, Lisp in particular is just unique. Anyway, C++, at some point you will have to do that to bring that one in. But the sort of Python, Java is an easy way in to get into.
Well, that's the sort of standard thing that we're sort of doing, but how do we then, you've been here advocating the advantages of Kotlin and Ceylon over that Java, so aren't we're missing out somewhere? And
that's because at the moment, Java has the motivation of being the implementation language of Minecraft.
Yeah.
And that gets people going. Minecraft extensions, do not underestimate the power of Minecraft extensions as a way of teaching people programming.
Yeah.
And that means either Python or Java. And the motivation that that brings to kids learning stuff, do not underestimate it. And that's why Python Java is a good way forward.
So
We carry this on outside.
sorry, just to say that I thought it was with Scheme and Lisp it was about, was it 25 or 30 years? There's sort of 25 generational sort of period from having a really good go at redoing a language. And I think this is about right here too as well, isn't it? It's about that time. I don't know if there's any other examples.
I think Kotlin is challenging Java.
Sorry?
I think Kotlin is challenging Java after only 5 or 6 years of being mainstream, which is very interesting. But I'm quite happy to bring this to a close as suggested by past chair.
Okay, thank you very much again. We conclude the session and continue outside with more discussions. Food and wine. Very entertaining. I never seen such animated kind of things with graphic enter to the slides.
Right, let me just close this down.
Yeah, absolutely. That's what we do.
Well, now I think I have a good chance to have it here because
I can claim that I have programmed Python with France.
today.
Okay.
And now we will go
Better than I am.
So nice.
But
Okay, right, okay. So,
we will one of them probably will be very
okay. So it's-
Because unfortunately,
so we have a
some
strong
of these
transfer
things
agency.
always
Gives you an email anyway. And the other thing.
tinkering around and trying to understand
I don't
it.
believe we have rules, and I don't know, because this time I didn't.
We
find-
don't have any set for October.
Okay.
So we need to really urgently do something.
I just
Kind of stayed away from
find
my
Russel
last time. Very,
Yeah, no, but I mean, you've got to be doing this stuff.
Okay.
Hi, how you doing? How you doing?
What's it?
Good. Yeah,
that's,
all right.
that's the
That's why.
advantage.
See you outside in a bit.
See you, yeah.
Yeah. I think things have moved on a lot.
Yeah, I mean,
The only thing I would add is that, I mean, what we're getting, I think what you were saying basically was that types should all behave in the same way rather than define, but they're built in or different processes.
I mean, there's a
Which is so bloody obvious.
yeah, and it's the point that the chap at the back was making is that if you view object-oriented in the way that C++ and then Java try to mould it, change the definition,
Yeah.
then clearly Java is object.